Hello and welcome. Now, you might think biotech and computer graphics are worlds apart, but they are actually governed by the same invisible laws. Today, we, Group 12, will explore the physics of motion and heat. We'll show how the same principles that spin the laboratory centrifuge can also render realistic rotations in the digital world.
In biotechnology, we use the polymerase chain reaction (PCR) to copy DNA, but at its heart, PCR is a masterpiece of thermal physics. Phase 1: Denaturing. We raise the temperature to 98 degrees Celsius. In physics, this high thermal energy increases molecular vibration, providing the work needed to break the hydrogen bond like these two buses pulling the DNA strand apart. Next is annealing. We lower the temperature to around 60 degrees Celsius. As thermal energy leaves the system, entropy decreases locally, allowing the primer and template DNA to stick together through stable bond formation. Finally, elongation at 72 degrees Celsius. This specific temperature provides the optimal kinetic energy for the Taq polymerase enzyme to add new rails or nucleotide to the DNA strand. By controlling heat transfer and thermodynamics, we can turn a single DNA fragment into billions.
For the next part, our group chose rotational dynamics topic to showcase its application in biotechnology course. The topic is applied in our biotechnology apparatus, which is centrifuge. Centrifuge is used to separate particles like cells, organelles, or DNA from a liquid by spinning the sample at extremely high speed driven by a force resulting from object's inertia, as it falls into circular path. The core physics concepts here are centripetal acceleration. The centrifuge will rotate around a central axis, create rotational dynamics. This rotation will create a centrifugal force. This centrifugal force will act on particles, causing the particles experience greater force, causing denser and heavier particle moves outward faster and separates from the liquid easily.
So in physics, we describe rotational motions using three axes, x, y, and z. This represents our three degrees of freedoms, the ability to tilt, turn, and spin in 3D space. But whether you are a NASA engineer or a 3D animator, you're fighting a common enemy, which is a gimbal lock. Gimbal lock occurs when the meter rotation's axis keep up by 90-degree angles, causing the other two axes to point in the exact same direction. So mathematically, we lose a dimension. Our 3D world collapsed into 2D world now. So now, spinning and turning performing the same motion, causing the system to lose control and spin chaotically. But in mathematical computer graphics, this is a totally nightmare because the maths collapse into the computer gets confused right now. To get from one pose to the next, it's forced to calculate a real 180-degree flip in a single frame. So this will turn a heroic animations into a jerky digital disaster. In drones, this is also a disaster. When the camera points straight down, two rotational axes align and lock, so the max fails, forcing the models to jerk 180 degrees instantly to find their way. So this will cause a violent vibrations, shaky footage, and can even lead to a mid-air crash. So how do we fix it? We ditch the rings and use quaternions. Instead of calculating rotations in three separate steps that can overlap, quaternions look at the rotation as one smooth direct arc. No overlapping cracks, no glitches, just a perfect continuous motion in every frame. So by mastering the physics of rotational, we just don't glitches, we build the world. Understanding the max keeps the digital world moving. Thank you.
Did you ever wonder why 3D renders look grainy or noisy before they become a masterpiece? It's because the computer is fighting a law of physics called entropy. In the real world, light is naturally chaotic, but in the digital world, we have to use the second law of thermodynamics to turn that chaos into realism. In physics, entropy is just a second word for disorder. The second law of thermodynamics tells us that everything in the universe naturally moves towards a state of messiness. Imagine energy constantly spreading out. That's entropy in action. Think of a beam of light the moment it hits a wall. It shatters into millions of randoms and predictable directions. In the real world, light is naturally chaotic. To create realism in the digital world, we have to use math to tame that chaos. In computer graphics, we have a similar problem. To create realism, we use Monte Carlo rendering.